The inductor is an energy storage device. Once we get past the storage phase, the inductor actually looks like a short circuit. So the inductor in steady state, meaning nothing in the circuit is changing anymore, equals a short circuit. Okay, you can just replace it with a wire to do your circuit analysis. So let's actually look at an example here, number 6 that I have. We're going to redraw the circuit. This is really important. You always want to redraw the circuit to show what's actually happening in steady state. So that's what I'm going to do right here. I'm going to redraw my circuit. So I've got my voltage source, my 20 volt source. I'm going to short out L1 because I'm assuming the storage phase has passed, and once it has passed, there's no opposition to that current anymore, so it's just going to be a short circuit. And then I've got my R1, my R2, L2 becomes a short circuit, and here I've got my 4 ohm R3. So R2 and R1. Okay, so what we're looking for here is we're looking for the current through L1 and the current through L2. So the inductors are still there. Okay, so there's still an inductor here that is L1, and there's still an inductor here that is L2, but the way they're behaving at steady state, they look like a short circuit, so I draw it that way. Alright, so let's figure out what L1 and L2 are. So we've got basically a series parallel combination circuit here, so I'm going to combine my R2 and R3. Those resistors are in series. So I'm going to add those. So 6 ohms plus 4 ohms, I've got 10 ohms of resistance there. I did not do anything with R1 just yet. So I'm going to remove the 6 ohm and the 4 ohm resistive branch, and I'm going to replace it with their equivalent 10 ohm resistor. So I'm going to just call that RA for now, and that's going to be 10 ohms. So at this point I can combine R1 and RA. They are in parallel, and I'll call that RT because that's our total resistance of our circuit now, as seen by the source. So 1 over R1 plus 1 over RB. So that's about 2.86 ohms. Okay, so that's step 1, step 2, and then I'm going to draw my simplified circuit to represent the fact that I've got 20 volts of voltage applied to my circuit, and I have a total resistance of 2.86 ohms. We do that so that we can find our source current, of course, which is E over RT. So 20 volts divided by 2.86 ohms means we have 7 amps of current. So I'm going to draw that in right here, 7 amps. I'm going to step back through the circuit just like we learned to do when we analyzed series parallel circuits. So I've got 7 amps here. Now, when we get back to step 2, we have split apart our total resistance into parallel resistors. And we know that parallel resistors have the same voltage drop across them. So both of these resistors are going to see 20 volts voltage drop across them because they're in parallel not only with each other but with the source as well. remember, parallel means that they're connected on one side and connected on the other. So parallel resistors are connected on both sides. So what that allows us to do is find our currents. So I1 is going to be V1 over R1. So let's look at right here at our resistor R1. V1 is 20 volts. We have a 20 volt drop across the resistor, and we've got 4 ohms of resistance. So that means I must have 5 amps of current through there. Whoops. Let's put that back real quick. Okay, and then so we've got 5 amps here. Then let's look for our current I2, or no, I'm sorry, IA, because we called that resistor RA. So that's going to be the voltage drop across A divided by RA, where that voltage drop is 20 volts and RA is 10 ohms. So we have 2 amps there. So 2 amps this way. And if you remember your Kirchhoff's current law, we have 7 amps coming into this node, 5 amps going this way, and 2 amps going the other way, and that makes sense. Okay, so let's move back up one step in our circuit, and we see that we've got 7 amps here, 5 amps here, 2 amps here. Now, we could go ahead and calculate our voltage drops across R2 and R3. That's all that changed here. So 2 amps times 6 ohms, we've got a 12 volt drop here, and that same 2 amps times the 4 ohm R3 means we've got 8 volts drop there. Truthfully, we didn't really need that because we were just looking for I1 and I2, and we already have that. So I1 is actually the source current in this case, equals I sub S, and I2, notice, is actually I sub A. So in this case, I1 was 7 amps, and I2 is 2 amps. Because we were just asked for the current through each of our inductors. So the current through I1 was just the source current. The current through L2 was just the current also through R2 and R3. Let's look at another problem. If you want to try this one yourself, go ahead and hit pause. Just remember, as you're redrawing your circuit, that in steady state conditions, your inductor equals a short, and your capacitor equals an open circuit. You've got both in this circuit. So go ahead and pause, try redrawing your circuit at least, and then hit play again and see if we get the same answer. Okay, so I'm going to redraw the circuit here. I've got a 60 volt source. I'm going to replace this with a short circuit, and I'm going to replace my caps with open circuits. Oops, I do need that resistor in there, at least for the time being. Okay, and we're looking for all the unknowns. We're looking for V2 and V1. We're looking for I2 and I1 right here. Okay, let's fill in everything else we know about our resistors. I've got 60 volts there. Alright, so the first thing you always want to do when you analyze the circuit is trace the path of current through the circuit. Now in this case, notice that you have an open circuit here and an open circuit here. That means there's really no path for current to get from the positive terminal back to the negative. So that means that your I sub S is 0 amps. So when we're looking for I1 or I2, they're simply 0. No current anywhere in the circuit. There can't be any current through our inductors. Okay, so now we're looking for V1 and V2. Well, it turns out this is pretty simple too, because if there's no current through our resistors, there's no voltage drop there either. They might as well be short circuits. So for V1 and for V2, they are both essentially connected to the positive terminal of the source and connected to the negative terminal of the source. So in this case, both of them are 60 volts. So we'd see 60 volts across each of those caps. Fairly simple, but again, you're going to have to really work at getting down the open and short circuit ideas here. Okay, let's look at number 8. And again, I'm just going to redraw it. If you want to pause and redraw it first, go right ahead. But I'm just going to redraw the circuit with, again, in steady state conditions. What that means is your inductor looks like a short circuit and your capacitors look like an open circuit. So I'm just going to redraw my circuit here. I'm going to go ahead and close that switch as if it's been closed a while. And here's the circuit. So I'm looking for V1 here and I1 here. I'm looking for I2 this way and V2 over here. Okay, let's see if we can do a little circuit analysis here. Again, always try to track that path of current. So if I had current, it would be leaving here. And again, remember, if you're a little uncomfortable with this notation for the source, this is really nothing more than saying there's a source out here that is 12 volts with respect to ground. And then you can connect ground up. So really, this is the circuit you're looking at, but I'm going to take that back out just to try to get you a little more familiar with this notation. Okay, so, and again, these grounds are connected. So you can just kind of imagine they're connected in your mind. So if we do have current coming from the source, all of it's going to go to ground and then back to the source. There's not going to be any current through I2. So I2 is going to be 0, really because there's an open circuit over there, and we know that there can be no current through an open circuit. So I2 is 0, but I1 is not 0. How do we calculate I1? Again, I1 is going to be the voltage drop. For instance, we have a resistor here that's a 4 ohm resistor. I should have put in the resistor values. So to find I1, we would take V1 divided by R1. And V1 in this case, if you notice, whoops, I'm going to have to redraw some things here. V1 in this case is just the voltage drop from here to ground. So we've got 12 volts there because of the source. So that's going to be 12 volts divided by 4 ohms, or 3 amps of current here. Like I said, V1 is just 12 volts because it's the voltage from this point to this point, where this is connected to our positive 12 volt source, and this point is connected to ground, where we assume voltage is 0. So we already discovered that I2 has to be 0 amps. So V2 would be the current through the 8 ohm resistor, which in this case would be I2, except there's an open circuit up here. So we still have 0 current through that 8 ohm resistor. So that's just going to be 0 volts. Let's look at another circuit, and if you'd like to draw this one and work the problem yourself, go ahead and hit the pause button there. I'm going to redraw the circuit. Over here, again, we're looking at steady state conditions, which means we're just going to take any inductor and make it just a piece of wire. We're going to take any of our capacitors and remove them from the circuit right where they are. So basically for our inductor here, that's going to become a wire. The inductor here will become a wire. And then my capacitor, I'm just going to take out of the circuit and leave that open. So as I redraw, there's my open circuit and my wire for my first inductor. So I've got 6 ohms here, 3 ohms here. This would be my inductor, but it's in steady state, so it looks like a short circuit. And then here would be my capacitor. I opened that up, and here would be my L1. So I shorted that out as well. Okay. So here's really a model of what's going on in the circuit physically once we get to steady state. Of course, it all matters when we're talking about. So in steady state, this is what's going on. So here we've got V2, we have I2, V1 right here, and I1. So let's work on our circuit analysis here. This is really just a series parallel circuit at this point. So let's start combining resistors. So here, start as far away as you can get from the source, because that's where you typically find your parallel or series combinations. So here we've got a 3 ohm and a 6 ohm resistor. So that's going to combine in parallel to be 2 ohms. I'm just going to do a quick redraw. Everything stayed the same except for my 2 resistors in parallel there on the end. So I'm just going to replace those right here. So I've got my 2 ohms, my 3 ohms, 5 ohms here, 20 ohms here, and 50 volts. Okay, so at this, that was the first step. This is the second. Okay, so on the second step, let's talk about what we've got here. We've got this 5 ohms of resistance here. Those are in series, so I'm going to call that RB. And let's do a quick redraw again of the circuit. The 20 ohm resistor is still here. There's my 5. And then I'm going to remove the 3 and the 2 in series and add the 5 ohms RB out here. And let's talk about what we want to do next. All right, so next you might want to combine those 2 5 ohm resistors in parallel, but keep in mind they are connected up here. But what's going on the other side? This 5 ohm resistor is connected to ground. However, this 5 ohm resistor is connected to the open. So it really isn't going anywhere. There's no current through that 5 ohm resistor. So I'm just going to take it out. And what you're left with is a 20 ohm and a 5 ohm resistor in series. So your RT is just 25 ohms at this point. I could reduce it and draw the more reduced circuit, but I'm just going to leave it like this because I think we can do whatever circuit analysis we need to do at this point. So let's calculate our source current. That's why we reduce and return anyway. So I sub S is E over RT. And in this case, at steady state, our RT is 25 ohms. So we have 2 amps of current here. So I'm going to draw that into our reduced circuit. And let's find our voltage drops. You should know how to do this now. If we've got 2 amps through a 20 ohm resistor, Ohm's law tells us that that would be 2 amps times 20 ohms, or 40 volts. Okay, so I should have 40 volts there. That same 2 amps continues after the 20 ohm resistor to continue through my 5 ohm resistor. So I've got 2 amps of current there through 5 ohms of resistance. There's the other 10 volts, right? Kirchhoff's voltage law says that my 50 volts that I apply to the circuit should equal the minus 40 minus 10, and it does. Okay, so Kirchhoff's voltage law is upheld. So I'm going to transfer everything I know from step 3 up to step 2. And remember, there's still no current going through here, so I don't really even need to worry about that. It's just 2 amps throughout this circuit here. So I've still got 40 volts across here. And then this 10 volts is now going to divide between the 3 and the 2 ohm resistor because they're in series with each other. That's how we got our 5 ohms down here. But I'm just going to calculate the voltage drops across each. I've got 2 amps through 3 ohms of resistance, so that means I have 6 volts there. 2 amps through 2 ohms of resistance is 4 volts there. And remember that 6 plus 4 adds up to the 10 that I had down here. So those are a voltage divider. Transfer everything up to step 1. So I've got 2 amps here. Still 2 amps here. Again, no current through that 5 ohm resistor. 2 amps over here. Now, the current's actually going to split between the 3 and the 6 ohm resistor. So let's go ahead and put our voltage drops up here. So we had 40 volts drop across the 20. I had 6 volt drop across the 3. And then this 4 volt drop is across both the 3 and the 6 ohm resistor. Why? Because that's where I got the 2 ohms from. I combined the 6 and the 3 in parallel. In parallel, they have the same voltage drop, which is going to be that 4 volts. So if we want to find the current through each, I2 is going to be 4 divided by 3, or 1.33 amperes. And the current through the 6 ohm resistor is going to be 4 divided by 6, or 0.67 amperes. Okay, so we've got 2 amps coming into this node, 1 1/3 amps this way, the other 2/3 this way. They'll come back together on the other side and be 2 amps over here. So at this point, I1 is right here, and I1 is simply the 2 amps of source current right here. What else are we looking for? I2 is right here, which is I2 here, so that's 1.33 amperes. And then we're looking for V2. Now V2 is going to be this voltage right here, so it's going to be the 0.67 amps times the 6 ohm resistor. Well, remember, that was just 4 volts, so that's just going to be 4 volts there. And we're looking for V1 right here, which is the open circuit voltage on the other side of that 5 ohm resistor. Since there's no current there, we're really just measuring the voltage drop here minus the voltage drop here. Well, this is 0 volts, right? So V1 is just going to be whatever the voltage drop is here. So V1, if we start here at 0 volts, and we encounter our voltage source, on the other side of the voltage source, we're at plus 50. We're going to see a voltage drop of 40 volts across here, so what voltage would we see on the other side? We're down to 10 volts there. So V1 is the 10 volts minus 0, or V1 is just 10 volts. If you want, you can plug this circuit into multisim, and you can actually take these measurements. You can measure the current here right before you get to the inductor or right after. You can measure this current before or after your inductor. You can measure your voltage across that capacitor voltage, and and so on. You can measure the voltage across the resistor and see that they should all be exactly as